Hello people, welcome back to the x64 assembly language series. Our goal is actually to write or to read a text file and be able to print it out using the functions that we created before. But in order to do that, to kind of see how our progress, or to help us with our progress, we're going to need some other functions. And so one of the functions that will be really useful to us is to create a function that allows us to convert a number into a string. And so in particular, we want to be able to convert an unsigned integer into a string. And so that's what we're going to do today, is we're going to write a conversion function. And so you can see I've already created this third directory for the third video in the series. And what we're going to do is go ahead and copy the assembly language program that we had from before and open it up. And we're going to create a new function, and our function is called to be UI to A, which will be unsigned integer to ASCII string. And so we'll create some documentation for this. UI to A converts unsigned int to string, base 10, and then it'll have inputs. RAX will be the string buffer, and RDI will be a number to convert. Our outputs will be RAX, which will be the string buffer with converted string. So that'll be our thing. So now we have to think about our strategy for converting this number into a string. And so if you think about, we could use, say, mod. So we could mod the number by 10, and that would give us the each digit. But if we did that, it would give us each digit in reverse order. So if we just created a buffer and filled that buffer with each digit that we found by modding by 10, that would give us the number that we wanted to reverse order. So we could fill out the buffer that way and then go through the buffer again and reverse each character. But it would probably be better to just fill the buffer correctly the first time, just filling it from the end to the beginning. And to do that, we're going to have to calculate how long the buffer needs to be. Now, we're going to assume that the user gives us a buffer that's actually big enough to contain the string of the number that they want to have. So we're not going to do any checks for that, and that will save us some space or lots of time in writing code. But the next thing that we're going to have to do is do a calculation. And so what we'll do is we'll handle a couple different cases first. The first is handle the case where the number is 0. So if the number is 0, we can just write the 0 character and then write a 0 after that in the buffer, and then just return the buffer. And so we can do that here, where we say, in fact, we probably don't even need to return the buffer, because the buffer is, we're not going to be updating the buffer at all. So the output will be the buffer is filled with the base 10 conversion. So handle the case where the number is 0. And so the way that we do that is we're going to move essentially the value that we want into that buffer, and then end it with a 0. So we're going to move into the address at RAX. In fact, we're going to move a byte value at RAX, and we're going to move it in. We're going to move the value that we want. And for that, we're going to need a ASCII table. And so we'll look over here, and we're going to need the character for 0. And so the character for 0 has a decimal value of 48. So we're going to write that over here. So we're going to move 48 in there, and this will set the first char to 0. And then the next thing that we'll do is we will increment RAX, and I believe the increment instruction increment by 1. Yes, so we can do an inc, and of course I guess it has to be done on a 16 or 32-bit register, but that's fine. So I guess we'll increment EAX, move to the next char, and then we'll set that to 0. So we'll move a 0 into there. So byte rax 0, 0 terminate the string, and then we can actually go to the end of the thing. So we're going to say go to UI to A end. And so at the very end of this function, we'll have a UI to A end label, and that will allow us to go to the return instruction. So this allows us to just skip to the end because we've done everything that we need to do. The next thing that we'll want to do is we'll want to handle all the rest of the cases, right? So we know that we're going to have at least one digit, and we want to count the number of digits. So we're going to count the number of digits required for that conversion. And the way that we're going to do this is we're going to just have a counter that keeps track of this. And so we're going to use RCX for this. And so we're going to do a XOR on RCX. And that's because RCX used to be called ECX, and it was used as a counter. So the original x86 instructions, which used to be CX, or is used as a counter, and so we're going to use that here as a counter, and we're going to count up, or we're going to increment that counter for every digit that we see that's going to be in our number. So counter for the number of digits. And so how do we count this? Well, what we have to do is we have to essentially divide our number by 10. And we'll take the remainder, and that remainder is the digit, minus the amount that we need to add in the ASCII table to bring it up to the size of a printable digit. But we'll take that, the remainder will be the digit that we want to save, and then the amount that we divided by, right? The divisor or dividend is the number that we're going to continue dividing by. And we're going to divide it by 10 every single time, and we're going to keep dividing until we get to 0. And so that will allow us to calculate all the digits. And once we divide that number, say we have a number 127, we're going to divide it by 10. Its remainder is going to be 7, and so we will record that digit, or we're going to increment our counter, and then we'll keep dividing by 10 until we get to 0, and that will tell us how many digits that our number has. So what we'll have to do is, in order to not lose the number that we have, we're going to have to create a copy of that number. So we'll just create a copy of that number to, let's see, so our RDI has the number that we have. Oh, the other thing that we'll have to do is division requires certain registers to be used. So in order to set ourselves up to be able to use the registers needed for division, we're going to have to save our string to another table. So what we're going to do is move string address into another register. And so we're going to go ahead and do that. And we're going to move RDX. Let's see. What are some good other registers we'll use? Let's use RSI. Or even RDX. Yeah, let's use RSI. So we're going to move RAX and RSI. So move the buffer. Let's see, move the string buffer to RSI. So that will save the string address into another buffer. And so that way we can use RAX for division. And that's because if we go to the instructions and we say divide, there should be, that's fdiv. There should be an integer division. Here we go, integer division. And it looks like we need RDX and RAX. So those are the two registers that we're going to need. So hopefully we're not using RDX. You were using RSI. Good. So RAX and RDX, we can use, actually div will give us an unsigned divide. It doesn't quite matter in our instance. So we'll just use div, which will have RDX and RAX. And I believe what it does is it divides RAX by RDX, and it stores the results in both those registers. So I believe that it restores the results of the division in RAX, and I believe it stores the remainder in RDX. So just to make sure, let's look that up. So let's do x64 div instruction, and hopefully we'll find a good page for that. Here we go. So this does an unsigned divide, and so it uses AX, DX, EX, and RDX and RAX. Okay, so the source operand is the divisor, and so it RDX. Here we go. The source operand can be a general purpose register or a memory location. The action of this instruction depends. Okay. The division using 64-bit operand is only available in 64-bit mode. Okay, here we go. So yeah, divisor, quotient, and remainder. So, and here's the dividend. So the dividend will be RDX, RAX. The quotient will be RAX, and the remainder will go into RDX. Okay. So if I understand this correctly, then that means that dividend, and the divisor, the divisor can be any register, any 64-bit register. Okay, that's cool. But RAX and RDX will be the where the quotient and the remainder is stored. So that's very good. So we'll use RAX, which that also means that we will copy our value because RDI has our number to convert. And so what we'll do is we'll set up our, we have to put our number into RAX. So move, or say copy our number into RAX to count number of digits. So we're going to move into RAX the RDX value. So that gets us all set up. So now we can count the number of digits, And what we'll do is we're going to create a, whoops. We're going to create a label here that will be the loop that we have. So UI to A loop. And so we'll be able to come back up to this every single time. So what we'll do is we will first do a division. So let's see that we have this. So we have our counter set up. We have our number set up. Now we want to also set we need to set our quotient up. So setting up the quotient, we're going to move into, we can pick whatever register that we want that we haven't used already, but we probably don't want to use RDX. Oh wait, this is RSI. Whoops. So RSI, there we go. So we're gonna move a number into a register that will be our divisor, and so we need to move, our divisor is going to be 10 every single time, so we won't have to change it, but we're going to pick a register for that, and the register we're going to pick is, let's see, let's look at our system calls. Let's pick our 10. Nobody's using that. Are we using RDI? I don't think we're using RDI, so let's do RDI. I'm going to move 10 quotient. So then what we can do is we can say we're going to divide RAX by RDI, divide the number by 10, and what will happen is we're going to get RAX will now have 10 times less than what it had before, and RDI will have the digit that, or RDX will have the digit, but we're not interested in that yet. So the other thing that we're going to do is we're going to increment our count. So we're going to increment our CX by 1, and then let's see, because if we said, oh, let's do EDX, oh, CX by 1. So increment the count by 1. And then what we're going to do is we need to jump. We need to continue doing this loop as long as RAX is greater than 0. So let's look for a jump instruction. So jump if greater than, oops, not around here. Jump if greater, jump greater. There we go. Jump short if not less than or greater than. Jump if, is there, let's see if we got like a GZ. Here we go. So we've got a bunch of different jump instructions. So we're going to say, let's just pick one. Jump short if 0. Jump short if not 0. So we're going to jump short if not 0. So we want J and Z. So we want to jump if something is not 0. So jump not 0, and I believe we'll give it a relative value. And I believe that the division instruction will set the ZF flag. So we'll check to make sure. So, and we're going to jump back to UI to A loop. And so let's check on that divide instruction. So there should be, it should tell us flags affected. So the ZF flag is affected. So it should tell us if our quotient, is it our quotient? Yeah, it should tell us if our quotient is 0 afterwards. So that should work. So hopefully that'll work. And so that will give us a loop that now we have counted the number of digits. So RCX should now have the number of digits that are required for our string. So now what we can do is set the pointer to the buffer, to buff, to be RCX number of digits in. So that's what we'll do, is what we'll set. We'll add to the to our buffer, and our buffer now is stored, I believe, in RSI. So we'll add to our buffer address. We're going to add RCX to it. So increment buffer. And so the reason why we're doing this is we're going to the end of the buffer that we need. And then what we're going to do is we're going to set the terminating 0, and then we're going to fill in each digit backwards and work our way towards the front of the string. So let's go ahead and do that. So now we set our pointer, that number of digits. Now let's see, we're going to start with 0, and let's just say that we have 127. And if we divide it by 10, we'll get 12, and our remainder will be 7, but we don't care about that right now. And we'll increment our ECX by 1, so now we've got 1 digit. And then if we divide it again, we'll go from 12 to 1, and we'll increment our ECX again. That will give us 2 digits, and then we divide 1 by we'll divide 1 by 10, and that will give us 0. And that will give us 3 digits there. So the thing that we'll probably want to have before or after this loop then is we want to add one more number onto that, because we want to make sure that we terminate our string with a 0. So add one more, or increment ECX by 1 to move to 0 terminator of string. So we're going to increment ECX one more. So now then we'll set our buffer to the end of the string. So now we've set our buffer. Then we can write the terminating 0 to the string. And the way that we'll do that is we'll move into the byte at RSI. We'll move the terminating 0, which is just a 0. And so now what we can do is we can just convert loop through the number and convert to string. So, and we'll start another label, which will be UI to a convert. There we go. And what we'll do with this is we'll do essentially the same thing that we did in the UI to a loop. Except we're going to care about the remainder. So we can do, we also need to set up our number again. So we're going to do that, and we're going to say move into RAX, because RAX is now 0. We need to move that number back in, and we're going to move that number in to RAX. And the way that we'll do that is let's see, RAX, copy our number into RAX. Ooh, do we have so we moved the string from RAX to RSI, But let's take a look at our system calls. RSI. Do we have a... So wait, RDI is where our number starts out. So RDI is where our number starts out. And we're going to move the string to another register. So we'll remove the string to RSI, copy our number into RAX. Oh, this is a typo here, right? So because RSI basically has our string, right? And RAX needs to actually have the digit that we're storing. And so the digit that we're passing in is actually in RDI. So RDI has our number, and so we're gonna move that in, and then our quotient can become RDI now. So that sets things proper. Now, then, so then if we go through here, RAX by RDI, so that's good. Now, but the thing is, we need to have one more place where we store our number because we're using RDI as our quotient. Unless maybe we don't use RDI as our quotient. We could use we can't use RDX because that's where the remainder will be stored. We could use R10. That's probably the cleanest way to do this. So let's go ahead and use R10 to store the quotient. So, and that kind of makes sense because we're going to store 10 in R10. It's kind of a poetic thing. So we'll use R10 here. So that way RDI will continue to have the copy of our original number. So that way we can set RAX with RDI. So reset RAX with the original number. So now RAX has the original number that we had, and we can now loop through the number and convert it to a string. So we'll do like the same thing that we did before. We'll divide RAX by R10, which will divide by 10. And then RAX and RDX will have the numbers that we have, but this time we care about the digit that we're saving. So RDX will have the digit that we're interested in. Now the digit is the actual number. So the digit might be 7 or something. And what we have to do is we have to add a constant amount to that number in order to make it a printable number. So if we look at the ASCII table, let's say that we have the number 7. In order to make it a printable 7, it needs to be it needs to be basically 48 plus, right? So we'll have to add 48 to whatever 7 was before, and then that will give us a printable 7, right? So that's what we're going to do is we're going to add to RDX, we're going to add 48 to it, convert digit to ASCII character, and then we can save that ASCII character into where our string is pointing. Now, we've already set our character for our string in RSI. So what we're going to do is we're going to decrement, we'll say ESI since we're limited to like a 32-bit value. Move the buff pointer back by 1. And so we're going to do the same thing here is we're going to move a value into the byte of our, let's see, was it RSI? Yes. So we're going to move a byte value from RDX. So move character into buffer. So that allows us to set the character that we have. Then we can decrement. RSI. Move buffer to next char. And then what we're going to do, in fact, we don't want to move beyond the buffer. So maybe what we'll do is, instead of decrementing here, we'll decrement at the beginning of the loop. Okay, so then we'll also decrement decrement ECX. And actually, I think we may be able to even get away with not doing that, because there should be a loop instruction. Okay, here we go. So there is a loop instruction. We can decrement the count and jump if not 0. Okay, so I think that'll work. So if we loop not 0, we're going to go to UI to A convert. So what this will do is this will actually jump a short relative value. Let's see. Nice. So this does RCX, decrement count, jump short if count does not equal 0, and the ZF flag is 0. Okay. So I think, let's see. So hopefully this will work. So this allows us to have a, so let's see. We've got decrement RSI. So we're going to move our pointer to the buffer. We're going to divide by RAX by 10. We're going to add to the remainder of the digit. And then we're going to move that digit into the string value over here. Then we're going to check. We're basically going to loop if not 0. So this will decrement the count. And remember, the count register is RCX. And we've already preset RCX up here in this loop to have the number of characters that we care about. So this will let's see. In fact, RCX. In fact, ECX, we don't have to increment it again. Set the pointer to be a number of digits. Oh, we do have to do that. Okay. So then what we'll do is, after we move that byte in, then we'll actually decrement our ECX, because we want it to be the number of characters that are left in the array. So dec the count. Let's reset the since we set the terminating 0. And I'm gonna check this again. So is there a, like, going for dec, let's search upwards. Register 16 or 32. That's kind of crazy that you can only do 16 or 32-bit registers for decrement. But I guess that makes sense. Okay. So let's go, and we're getting very close to the end of this, to where we can start testing it out. So let's think about this for a second. We're going through this loop, very short loop. We increment the x, set the pointer, write the terminating 0, and so now let's say we had 3 digits, we'll increment this to 4. Then we will increment 4 digits into our buffer, and then set the terminating 0, and then we'll decrement ECX. So now we're back down to 3. So we're going to write our 3-digit number. So this UAI convert will actually decrement our buffer, because our RSI still hasn't been decremented up here. So we're going to go ahead and do that here. So it'll go from our terminating 0 to the first character that we want to write. And then we'll divide our AX by 10, which will give us the remainder, and we're going to take that remainder and we're going to add 48 to it, which will convert it into a character, and then we'll save that character into our string. And then we will do a loop in Z, which will decrement our CX, check if it's 0 yet. And if it's not 0, then, or if it is, if it's not 0, it'll go back up. And then if it is 0, then we'll go to the end. Now, will this be a problem? Let's see, because if we write the first character, we go from 3 to 2, and then we'll write the second character, we'll go from 2 to 1. We'll write the third character, we'll go from 1 to 0, and that should be okay. So I think this will actually be okay. Let's try this out. This is a lot of stuff to run. So we're going to use FASM to assemble, and this go to, oh, UI to A. Oh, yeah, because we're not in C. I can't believe I wrote go to. So this will actually do, we'll just do a jump. And in fact, what we'll do is, in fact, we don't want to jump to the, we don't want to do an unconditional jump. What we want to do is we want to set the first character. Oh, handle the case where the number is 0. So this is where we're going to, we need to check if the number is 0 first, right? So we didn't check for anything here. So what we need to do is we need to check and see if the number that we're trying to convert is 0. And if it is, then we will continue on to this. And then this will just jump us to the end, right? So what we'll do is we'll check and see if this is 0. If it is, or if it's not, then we'll actually do convert regular, UI to a convert regular. So we'll jump if not 0. And this will be, let's see, so I'm going to take a look at this. So if we do jump if not, wait, it's probably under jump here. We've got a bunch of different jump conditionals. Here we go. So J and Z, jump short if not 0. So this is the 0 flag. So we need to be able to test if something, we want to do a test of a number. Let's see, instruction, relative 8. Okay, so we need something. We need to do something to set this 0 flag, or you know, basically unset it if it. We need to have like a test for 0. So what we're going to do is we're going to do a test. Let's see. Can we do like a compare? So we're going to compare two operands. And this will allow us to set the flag that we want. So we're going to compare, say, RAX to an immediate 32. So that's exactly what we want to have. So we're going to do that. So we're going to compare. Oh, and it has to be RAX. That's interesting. Okay, so we're going to compare first. So we're going to compare, and we have to compare RAX. So RAX is, oh, this is really interesting. So RAX has to hold the number that we have. And right now RAX is the string buffer that we have. So what we're going to need to do is we're going to need to preemptively at the very top of our instruction kind of move those two things around. So we're going to have to use a couple of these things. So we're going to move the string address into another register, and we're going to copy our number into here. So we're going to do these things. up front. Or in fact, just these things. So that allows us to do those things up front. So now we can get rid of this. And what this will do is now our string is in like a nice place. Our number is copied into RAX. So now we can compare RAX to 0. We can compare it to an immediate value. And then we can do jump if not 0 to UI to a convert regular. And I already see the typo. So there we go. So we'll convert UI to a convert regular. So if compared to 0, if it's greater than 0, we're going to just convert regularly. Otherwise, we're going to do these instructions. We're going to set the first character to 0 to a character 0. And then we're going to increment EAX. And oh, why are we incrementing EAX? Oh, because RAX has the string. So that's the other thing that we have to do. So RAX is no longer what we want it to be. It's RSI. So ESI and RSI. There we go. So that will set the string properly, right? So then, so basically, if this condition, if RAX is greater than 0, we're going to skip all this stuff and go down to our regular conversion, which will set our quotient and then do our counts and then do this loop, which will count. Do this loop, which counts the number of digits. Then we'll set this count properly, and then we'll set the terminating 0. And then we have the final loop, which actually converts all of the strings. So that should be our full function. And it looks like we still have a little problem. So let's take a look at this. ASM 83. Oh, are we not allowed? Let's see. There's something wrong. Division RAX by register 10. Oh, RAX is always going to be. Yeah. So okay. So let's show this. I want to show this. So let's go div. So we're going to show the div instruction here. Div, the instruction will only takes a single register or maybe a memory address if you're on the lower stuff here. So a register or a memory 64-bit, it only takes one operand. And the reason why is because the dividend is always RAX. So in fact, it's the RAX RDX pair. So what we're going to do, in fact, what we're going to do here is we're going to set, we're going to zero out RDX to make sure that the flags are properly set. So we're going to XOR RDX with RDX, make sure the remainder remainder starts at 0. And when we do a division, we're just dividing by whatever register that we want. But the register that we're dividing into is always RAX. So we're going to have to fix that over here. I had just forgotten about that. So let's set this here. There we go. So now we've got division FASM main. So we're getting closer. So move character into the buffer. Oh yeah, that's right. That's right. We can't, we're trying to move a 64-bit value into a byte. That's not going to work. So the operand sizes do not match in line 104. So let's go ahead and fix that because we're only going to be moving the byte. RDX, let's see, 32 bits will be EDX, 16 bits will be DX, and let's see, what is x64? X86 register. Let's look at the register cheat sheet, right? So it's easy to forget like the original like byte versions of these. So there's, oh yeah, that's right. So it'll be, so EDX, which RDX is the 64-bit, EDX is 32-bit, DX is 16-bit, and then there's a high and a low byte. So DL is what we really want in here. So we're going to load DL here. So that will move that into the correct thing. Now, is there anything else where we have a problem with that? I don't think so. Let's check. Okay, so it compiled, but that doesn't mean that it works. So, and in fact, all that we did was we just wrote the function. We haven't used it yet. So let's go back up here. And what we're going to do is we're going to take, let's go ahead and, well, let's just comment this stuff out, right? So we'll exit the program. So then at the beginning of the program, what we're going to do is we're going to move, and let's see, we'll have to create a buffer, right? And our buffer already exists. It's called buff, and we're reserving 80 bytes. And so we're going to move, let's see, our conversion function. We'll have RAX being our buffer, and RDI will be the number to convert. So RAX will have the buffer and move RDI with the number to convert, and let's just put the number to convert as 137. So, whoops. Then we can call UI2A, and then that should actually return. Well, it actually doesn't return any value. Our buffer will just simply have the value that it has in it. So then we can go again, and the number of bytes to write. So the number of bytes to write needs to go into RDI. Oh, that's an interesting thing. We should probably return the size. That would be a fun thing to return. Return the size in RAX. That of the size of the converted string. That's a really cool idea. So let's go ahead and do that. So we're in our documentation, we're going to say that RAX, the size of the converted string, or the number of digits. So what we're going to do is this RCX value, we're going to save this, and we're going to say RCX value to return the end of the function. So we're going to save this into a register, and we're just going to save it into, say, R8. That sounds like a good register to me. We've got a bunch of general purpose registers. Might as well do it into that one. And we're going to save RCX into that. And so then at the very end of the function, before we go to the end here, so this is the conversion, and then we'll we'll do a mov. In fact, what we'll do is we have to take care of the case where it was 0, right? So if it was 0, and before we jump to the end, we need to mov the size, which will just be 1, into RAX, be 1. Set the return num of digits. And then at the very end of the thing, we'll do the same thing here. RAX will be R8. There we go. So that should set that up. And that should be that. So now we can go back here, and RAX will actually have the number of bytes to write into it. So RAX will have the number of bytes to write. We can move, and that will go into RDI. RAX will have the buffer address after that, and then we can call write console, which should be able to write the number that we printed. So we should actually get 127 printed out at the end, hopefully. So if everything works correctly. So let's reset here. FASM main as there we go. And then we'll run main. And looks like we've got an infinite loop there somewhere. So we'll have to figure this out. There's an infinite loop here. And we have to figure out where it is. So this UI to A, let's move, jump. So the first one here isn't really a loop. In fact, let's test that one first. Let's test converting 0 and just see if that works. 0. Okay, so that works. So we don't have a new line at the end. We just end our string, so it's fine that it just prints here. So the 0 number works. So the next thing might be, say, 12 or something like that. And that means that there's a couple different places where we could get stuck. And one of them would be in this first loop here, which would Azure RDX and RDX. We div by 10. We increment the ECX value and jump if not 0. Oh yeah. Yeah, that's a problem. That's a problem because if we're incrementing ECX, I bet the increment, yeah, we're probably comparing with the ECX flag here on the increment, because if we do increment, let's take a look at increment. Okay, so increment by 1. This will probably, yes, it affects the ZF flags, and this will always be positive. Well, until it like overflows or something. This will always be positive because we're incrementing by 1. So this will never jump of 0. No, that won't happen. So what we have to do is we have to compare. So let's compare a register to 0. And so we're going to compare the RAX register because that's what we care about. RAX register, compare that to 0. And then that will allow us to break out of the loop. Now that means that probably we'll have to worry about this other conversion loop too. So we need to move something over here. Oh no, but this is RCX, so that should be okay. So FASM main ASM main. Oh, floating point exception. So you might think that this is kind of weird, floating point exception, because we're only doing integer division. Why are we getting a floating point exception? Well, that goes back to the division operator here. So we have to make sure that our flags are set properly. So let's take a look at div. So div, and I think they even have, actually they don't list it here. It's kind of funny. So in 64-bit mode, cannot be allowed to access, blah, blah, blah. Divides the value. Now I think what we have to do is we have to, doesn't it say exceptions? Obviously the source you can't divide by 0. Memory address, page fault, alignment, lock. Virtual, there's no like floating point exception. Oh, 64-bit mode exceptions if memory address, non-canonical form, the source operand, divisor is 0, which the quotient is too large, page fault. I think we have to clear let's go back here. So for our division, we have to make sure that, and I believe that, so let's see, RAX and RDX, so RDX, RAX. Now I believe that RDX, (64-bit mode), instructions divide the unsigned value in RDX, RAX by the source operand, and stores the quotient in RAX and the remainder in RDX. So yes, that's exactly what we thought. And so I'm clearing out the RDX so the remainder is fine. So I thought if I cleared out RDX, we should be fine. Operation, so if DE, then divide error. Else if double word operation. 32, here's else if 64-bit mode. Then temp equals RDX RAX divided by the source register. And our source register has 10 inside of it. If the temp is greater than this large value, then there is a divide error. RDX. So RDX, but I'm setting RDX to 0 when we start. Oh, but am I doing it up here too? I'm not. So I'm doing it here, but I'm not doing it here, which I really should. That's okay. Make sure the remainder starts at 0. Because I think bad things can happen if we don't do that. So let's do FASM main ASM main. There. So that worked. Now the only thing, it kind of worked, right? Because we got this first digit here. It's supposed to be 12, but we only got 1. So let's do like 23. Okay. So we're only getting that second digit there. That's very interesting. So I wonder what would happen so there's a couple different things. Either we're not like writing the character or the size that we're giving it is just too small, right? Maybe it's 1 too small. Oh, is the size that we're giving it 1 too small? Let's check that out. So what if we have 123? Okay. Okay, so it's just 1 too small, the size that we're returning. So let's do let's go down here, and we're going to move, I thought we moved RAX R8. So this, what we're going to do, where do we save it? We save into R8 here. So what we're going to do here is copy this. All right, so what we're going to do is we are going to increment this ECX anyway. So let's go ahead and do that and then save that value into R8. So that way when we return it, it'll have the proper number. Now, this, we still may be getting the wrong thing, but we'll see. Let's see, FASM main ASM 123. Okay, so that's good. So now let's try 1, 2, 3, 4. Okay, 1, 2, 3, 4. Okay, so now we're actually properly converting the unsigned integer into a string and printing it out. So that's very good. So we've accomplished the thing that we set out to do. Now it's kind of funny because you would think it's like, oh, just converting a number, it should be like super easy. I mean, it relatively is super easy. In C, you can do it in a very short amount of code. In fact, C just has, you know, it has a library function that you can just call I to A, and that will convert things for you. But even if you don't have that library function, you can do it very simply in C. But notice like how much code that we had to write. And I'm sure maybe if someone is an expert in assembly, they might be able to write something a little bit more compact than this. But we wrote a decent amount of code just to convert a number to an integer to a string, and not even a signed integer. We have an unsigned integer, right? So there's actually a little bit more code that you would have to write if you had a signed integer in here. But I thought this was interesting, and this will actually help us to actually debug our next thing that we're going to do. And the goal, like I said, is to create another function that will allow us to read a text file and then print out that in a string. And that will we'll do a bunch of stuff. We'll actually, instead of having a fixed buffer, we're actually going to have a buffer that we allocate. Right? So we're actually going to be returning a buffer that gets allocated. And so that'll be really interesting because we'll be using more system calls to actually allocate memory from the operating system, which was actually really interesting. It's actually pretty simple to do, but it's very interesting to see because a lot of the tutorials don't show you some of these more intricate things like, you know, dynamic memory allocation. So we're going to get to that hopefully next time. And until then, have a great